optocouplers, and its various applications.
Optocouplers, also known as optoisolators or photocouplers, have a wide range of applications across different industries due to their ability to provide electrical isolation while allowing for signal transmission through light. Here are some common applications of optocouplers. Signal isolation and protection. Digital signal isolation. Optocouplers are used to isolate digital signals in applications where noise or voltage differences could harm sensitive components. Analog signal isolation. They can also isolate analog signals, ensuring that signal integrity is maintained in measurement and control systems. Switching and control. Microcontroller and PLC interfaces. Optocouplers provide a barrier between low-voltage microcontroller or PLC, programmable logic controller, outputs and high-voltage or noisy loads, such as relays or industrial equipment. AC power switching. Optocouplers are used to control AC power loads, e.g., lights, motors, from low-voltage control circuits, enhancing electrical safety and isolation. Motor control. In motor control circuits, optocouplers can be used to protect the control circuitry from high-voltage spikes and inverter switching noise. Feedback control systems. Optocouplers are utilized in feedback control loops to isolate the control and sensing components, ensuring accurate feedback without introducing noise or interference. Telecommunications. Optocouplers are used in telecom equipment to isolate interfaces between different sections of a system, such as line cards, to prevent signal interference. Medical devices. In medical equipment, optocouplers provide galvanic isolation to protect patients and sensitive electronic components from electrical noise and voltage differences. Audio equipment. Optocouplers can be found in audio equipment to provide isolation between audio input and output stages, reducing ground loop noise and interference. Industrial automation. Optocouplers are widely used in industrial automation for signal conditioning and isolation in sensor and control circuits. Power supplies. They are used to provide feedback and control in power supply circuits, ensuring stable output voltage and current regulation. Isolated data communication. Optocouplers are used to isolate data communication lines, such as RS-232, RS-485, or CAN bus, in applications where noise immunity and protection are critical. Automotive electronics. In automotive applications, optocouplers are used to isolate and protect low-voltage electronics from high-voltage systems, such as in electric vehicle, EV, and hybrid vehicle power electronics. Safety-critical systems. Optocouplers are integral in safety-critical systems like emergency shutdown systems in industrial plants, ensuring that control signals are transmitted safely. Home appliances. In appliances like microwave ovens or washing machines, optocouplers can be used to provide isolation between control circuits and high-voltage components. Military and aerospace. Optocouplers are used in military and aerospace applications to provide isolation in communication systems, avionics, and guidance systems. The versatility of optocouplers in providing electrical isolation and noise immunity makes them valuable components in a wide range of applications where safety, reliability, and signal integrity are essential. The specific type of optocoupler and its configuration may vary depending on the application's requirements. Galvanic isolation is a technique used in electrical circuits to provide complete electrical separation between two parts of a system while allowing the transmission of signals or power between them. This isolation is achieved by breaking the electrical connection between the two parts and using a physical barrier or isolation component to bridge the gap. Galvanic isolation is important in various applications for several reasons. Electrical safety. Galvanic isolation is often used to ensure the safety of users and equipment. In cases where high voltage or high current circuits need to be controlled or monitored by low voltage circuits, galvanic isolation prevents dangerous electrical currents from flowing into sensitive components or personnel. Noise and interference reduction. It helps to prevent electrical noise, electromagnetic interference, EMI, and radio frequency interference, RFI, from propagating between different parts of a system. This is critical in applications where signal integrity is important, such as data transmission and telecommunications. Voltage level shifting. Galvanic isolation can be used to shift voltage levels between different parts of a circuit.
For example, it allows a low-voltage microcontroller to safely interface with high-voltage industrial equipment.
Protection against voltage spikes. Galvanic isolation can protect sensitive components from voltage spikes, surges, or transients that may occur in one part of a circuit. This is common in power supplies and motor control systems.
Ground loop prevention. In systems with multiple ground references, galvanic isolation can help prevent ground loops, which can introduce unwanted currents and affect the accuracy of measurements or signal quality. Isolation in medical devices. Medical devices often use galvanic isolation to ensure patient safety by preventing electrical currents from flowing between the patient and the medical equipment. Industrial control systems. In industrial settings, where electrical noise and safety are significant concerns, galvanic isolation is used extensively to protect control systems and sensors. Telecommunications. Galvanic isolation is crucial in telecommunications networks to ensure data integrity and protect against electrical surges or lightning strikes. One common component used to achieve galvanic isolation is the optocoupler or photocoupler, which was discussed earlier.
Optocouplers use light to transmit signals across an optical barrier, providing electrical isolation between the input and output sides. Transformers are another example of a galvanic isolation component, where electrical energy is transferred from one coil to another through electromagnetic induction without direct electrical contact. Overall, galvanic isolation plays a vital role in enhancing the safety, reliability, and performance of electrical and electronic systems in a wide range of applications. Signal conditioning is the process of manipulating and preparing an electrical signal to meet the specific requirements of a particular application or to enhance its quality for further processing. This involves modifying various signal parameters such as voltage levels, current levels, frequency, impedance, or noise characteristics to ensure compatibility with the components or systems downstream. Signal conditioning is commonly used in electronics, control systems, telecommunications, and measurement and instrumentation applications. Here are some key aspects of signal conditioning. Amplification. One of the most common signal conditioning tasks is amplification. When a weak or low-level signal needs to be boosted to a usable level for processing or measurement, an amplifier circuit is used to increase its amplitude. This can be achieved with operational amplifiers, op-amps, or specialized amplifiers designed for specific purposes. Attenuation. In some cases, a signal may be too strong or have excessive voltage levels for the subsequent components or systems. Signal conditioning can include attenuation, where the signal's amplitude is reduced to an appropriate level using voltage dividers or attenuators. Filtering. Filtering is essential for removing unwanted noise, interference, or high-frequency components from a signal. Signal conditioning may involve the use of low-pass, high-pass, band-pass, or notch filters to shape the frequency response of a signal. Impedance matching. When connecting two components with different impedance levels, signal conditioning can include impedance matching to ensure efficient power transfer and minimize signal reflections. Transformers and matching networks are often used for this purpose. Isolation. Signal isolation can be part of signal conditioning, especially in situations where electrical safety is a concern or to eliminate ground loops. Isolation techniques, such as optocouplers or magnetic isolators, are employed to separate input and output circuits while allowing signal transmission. Digital conversion. Analog to digital converters, ADCs, are used to convert analog signals into digital form for processing by digital systems. Signal conditioning may include ADCs to digitize analog data accurately. Signal rectification and conversion. Signal conditioning can include rectification, where an AC signal is converted into a DC signal, or vice versa, to suit the requirements of a particular application. Signal filtering. Filtering can also involve the removal of DC offset or bias in a signal to center it around 0 volts. Signal scaling and offset. Adjusting the range or scaling of a signal can be necessary to match the input requirements of downstream equipment. Offset adjustment may also be needed to shift the signal level.
Signal compression and expansion. In some applications, it's necessary to compress or expand the dynamic range of a signal to ensure that it falls within the measurement or processing range of subsequent components. Signal conditioning is crucial for ensuring that the signals collected from sensors or sources are suitable for processing, analysis, or transmission in various applications, ranging from industrial automation and telecommunications to scientific measurements and medical devices. The specific signal conditioning techniques employed depend on the requirements of the system and the characteristics of the signals involved. Noise reduction, in the context of electronics and signal processing, refers to the techniques and methods used to minimize or eliminate unwanted and undesirable electrical noise or interference from a signal. Noise can distort or degrade the quality of a signal, making it difficult to extract meaningful information or causing errors in data transmission and processing. Reducing noise is essential in various applications, including audio, telecommunications, data transmission, medical devices, and control systems. Here are some common techniques for noise reduction. Filtering. Low-pass filters. Low-pass filters allow signals with frequencies below a certain cutoff frequency to pass through while attenuating higher frequency noise. They are effective at removing high-frequency noise components from signals. High-pass filters. High-pass filters do the opposite of low-pass filters. They allow high-frequency signals to pass while attenuating low-frequency noise. They are used when the noise is concentrated at lower frequencies. Bandpass filters. Bandpass filters allow a specific range of frequencies to pass while attenuating both low and high-frequency noise. They are used when the noise and signal occupy different frequency bands. Notch filters. Notch filters, also known as band stop or reject filters, are designed to attenuate a narrow band of frequencies, effectively removing noise that is concentrated at a specific frequency. Digital signal processing, DSP. Digital filtering. Digital filters, implemented through software or digital signal processors, DSPs, can effectively reduce noise in digital signals. Various filter algorithms, such as finite impulse response, FIR, and infinite impulse response, IIR, filters, are used for this purpose. Adaptive filters. Adaptive filters can adapt to changing noise characteristics and adjust their filter coefficients in real time to reduce noise effectively. Averaging techniques. Moving average. A moving average calculates the average of a set of consecutive samples, effectively smoothing out noise that varies rapidly. Exponential moving average. This technique gives more weight to recent samples, allowing it to respond to noise changes more quickly while reducing the impact of old noise. Grounding and shielding. Proper grounding techniques and shielding can reduce the entry of external electromagnetic interference, EMI, and radio frequency interference, RFI, into sensitive circuits or cables. Differential signaling. In communication systems, using differential signaling, such as twisted pair cables, can help reduce the impact of common mode noise, where both signal and noise have similar voltage levels. Isolation techniques. Optical isolation, achieved through optocouplers or transformers, can physically separate noisy and sensitive parts of a circuit, preventing noise from transferring between them. Noise cancellation. In some cases, noise can be actively cancelled out by generating an antiphase signal, equal in magnitude but opposite in phase, and adding it to the noisy signal. This technique is known as noise cancellation. Noise-reducing components. Using components specifically designed to reduce noise, such as low-noise amplifiers, can be effective in applications where noise is a critical concern. Digital signal processing, DSP. Advanced DSP techniques, such as adaptive noise cancellation algorithms, can be used to remove noise from signals in real time. Noise reduction techniques are chosen based on the characteristics of the noise and the specific requirements of the application. Effective noise reduction is crucial for improving signal quality, ensuring accurate measurements, and maintaining the reliability of electronic systems in various fields. Feedback control, often referred to simply as feedback, is a control system concept used in various engineering and control applications to regulate or control a dynamic system's behavior. Feedback control systems rely on the measurement of a system's output and the comparison of that measurement with a desired or reference signal, set point.
The difference between the actual output and the desired output, known as the error signal, is used to adjust the system's inputs or control actions to minimize the error and maintain system stability and performance.
Here are the key components and principles of feedback control. System. A system is the physical or mathematical representation of the process or plant being controlled. It can be a mechanical system, an electronic circuit, a chemical process, or any dynamic system that changes over time. Control loop. Input. The control input is the signal or parameter that can be adjusted or manipulated to influence the system's behavior.
It is typically represented as a control variable, CV.
Output. The system output is the parameter or variable that is being measured and controlled.
It is typically represented as a process variable, PV.
Setpoint. Referenced signal. The setpoint is the desired value or target for the system's output. It represents the desired operating point or performance level for the system. The setpoint is provided by the operator or an automated controller. Error signal. Control error. The error signal is the difference between the setpoint and the actual output of the system.
It quantifies how far the system's behavior deviates from the desired state.
Mathematically, it can be expressed as error equals setpoint actual output. Controller. The controller is a device or algorithm that calculates and generates control actions based on the error signal.
It decides how to adjust the control input to minimize the error and bring the system closer to the setpoint.
Controllers can be implemented using analog circuits, digital controllers, or software algorithms. Feedback path. The feedback path is the route through which information about the system's output is fed back to the controller. This typically involves sensors or measurement devices that provide data on the actual system output. Actuators. Actuators are devices or components that take the control actions generated by the controller and apply them to the system's inputs. They can be motors, valves, heaters, or any mechanism that can influence the system.
Closed-loop control. Feedback control systems are often referred to as closed-loop control systems because they continuously monitor the system's output and adjust the control input to maintain or regulate the system's behavior. The feedback loop allows for real-time corrections in response to changing conditions. Stability and performance. Feedback control systems are designed to achieve specific stability and performance objectives. Stability ensures that the system remains bounded and does not exhibit erratic behavior, while performance criteria define how quickly and accurately the system responds to changes and disturbances. Proportional integral derivative, PID, control. PID control is a widely used control algorithm that combines proportional, integral, and derivative terms to compute control actions based on the error signal. It is known for its ability to provide both steady-state accuracy and fast transient response. Tuning. Tuning is the process of adjusting the parameters of the controller, e.g., PID gains, to optimize the system's performance, including responsiveness, stability, and robustness to disturbances. Feedback control systems are pervasive in engineering and automation, used in applications ranging from temperature regulation in HVAC systems to speed control in motor drives to process control in chemical plants. They play a crucial role in maintaining the desired behavior of dynamic systems in the presence of uncertainties and disturbances. Safety-critical systems are systems or components within a larger system whose failure or malfunction could lead to catastrophic consequences, including loss of life, severe injury, environmental damage, or significant financial loss. These systems are prevalent in various industries, including aviation, automotive, healthcare, nuclear energy, and industrial automation, where ensuring safety and reliability is paramount. Key characteristics of safety-critical systems include high consequence of failure. Safety-critical systems are associated with a high consequence of failure. The failure of these systems can result in fatalities, injuries, or other severe consequences. Examples include aircraft avionics, medical devices, and automotive braking systems. Strict regulatory requirements. Safety-critical systems are subject to strict regulations and standards imposed by government agencies or industry bodies.
Compliance with these standards is mandatory to ensure the safety and reliability of such systems. For example, the aviation industry follows DO 178C for software and DO 254 for hardware, while the automotive industry adheres to ISO 26262.
Redundancy. Many safety-critical systems incorporate redundancy, which involves duplicating critical components or functions to ensure that the system can continue to operate even if one part fails.
Redundancy enhances system reliability and fault tolerance.
Real-time operation. Safety-critical systems often require real-time operation, or responses to events or inputs must occur within strict time constraints. Real-time systems must meet specific deadlines to ensure safety and prevent catastrophic failures.
Testing and verification. Rigorous testing and verification processes are essential for safety-critical systems.
This includes extensive testing of hardware and software components, simulation, fault injection testing, and formal verification techniques to ensure that the system behaves as intended under various conditions. Fault tolerance. Safety-critical systems are designed with fault tolerance mechanisms to detect, isolate, and mitigate faults before they lead to failure. These mechanisms can include self-checking hardware, error detection and correction codes, and graceful degradation. Diagnostics and health monitoring. Systems often include diagnostic features and health monitoring to continuously assess the system's state and detect potential failures or degradation.
This allows for proactive maintenance and prevents unexpected failures.
Safety assurance cases. Safety-critical systems typically require the development of safety assurance cases or safety arguments that demonstrate how the system complies with safety requirements and standards. These cases provide a structured argument for system safety.
Human factors. Human factors engineering is critical in safety-critical systems design.
Consideration must be given to how humans interact with the system, as human error can be a significant factor in failures. Documentation and traceability. Extensive documentation and traceability are essential for safety-critical systems. Every aspect of the design, development, testing, and maintenance process must be well documented to ensure transparency and accountability.
Examples of safety-critical systems include
aircraft flight control systems, medical devices such as pacemakers and infusion pumps, nuclear power plant control systems,
automotive anti-lock braking systems, ABS, railway signaling systems, industrial process control systems in chemical plants.
The development and certification of safety-critical systems require a multidisciplinary approach involving engineers, safety experts, regulators, and domain-specific professionals to ensure that these systems meet the highest safety standards and minimize the risk of catastrophic failures.